In this tutorial, we're going to take a look at solving exponential function word problems that involve us having to solve for the exponent. Now, if you recall, in the general form of an exponential function, we've got f at x equals a, the initial amount, b, the base, and x is typically the number of time periods that are either growth periods or decay periods. And in these questions, that is the variable that we're going to have to solve for. Okay, so let's take a look at the first question. It says the number of rabbits in a meadow is increasing at a rate of 16% per day. If there are 20 rabbits in the meadow today, how long will it take for their number to grow to 500? Okay, so we're given some initial information. We're told that they're increasing at a rate of 16% per day. So when I set up the base, I know it's going to be 1.16. The initial value of 20 rabbits will go in front of that base. And then the target down the road that I'm looking for is I'd like their numbers to grow to have a future value or a final amount of 500. And the question is, what variable, x, or in this case, it could be expressed as time, do I need to put in there to make this equation work? Now, notice that the growth rate is expressed in per day amounts. So when we solve for the value of t, the units of time that we're going to be associated with that value are days. All right? Okay, well, two ways to do this. One is to guess and check, to just go ahead and start putting in values for t and keep shooting for values, evaluate the right side of this, and keep shooting for values until you hit something that is 500 right on. But a better way is to use logarithms to get an exact value. So let's just go ahead and solve this. And so the first thing we're going to do is we're going to move the 20 over to the other side, and we're going to get 500 divided by 20 equals 1.16 to the exponent t. Okay. We can simplify 500 divided by 20. We know that is 25. So that is equal to 1.16 to the exponent t. Now, because this is in balance, that is because we have an equation with equals in the middle, both sides are equal, we can do the same thing to both sides as long as we're consistent. So I'm going to take the log of the left side, and I'm going to take the log of the right side. And when I take the log of a value that has an exponent, we actually take the exponent and we'll move it down here in front of the logarithm expression. Okay, now what do? Well, the t is no longer in the exponent. Now it is down, on the main line just with the other values. So let's just isolate t. So we will take log 25, and I'm going to divide that by the log of 1.16, and that is going to give me a value for t. And if I put that into my calculator, I will get as an answer t equals 21.687 approximately. And I can then round that to the nearest day, and I can see t equals 22 days approximately. So that means that after 22 days at a 16% growth rate, those 20 rabbits will multiply into a population of 500. All right? Okay, let's take a look at a second example. Okay, this second word problem also involves a growth rate, but it is not given to us as a percentage. So for example, these hornets are growing at a rate of 25% every day, or every week, or every month. Instead, the problem indicates that the number of hornets in a nest triples, so that's a key word. And triples how often? Well, triples every 2 weeks. Okay. We are told the initial number of hornets in the nest is 40, and they are interested in how long will it take for their number to grow to 3,000. So I'm just going to color code these different values. So there's the 40, and then let's color code the 3,000 in sort of a copper color. And then we'll set up the equation. Now remember, the unknown value is time. Is this, how long is it going to take? And we are identifying the units in here, and it says triples every 2 weeks. So the unknown value that we're searching for is, number of weeks. All right, so I'm going to use the variable w to identify that. But let's go ahead and set up the equation. All right, so we have 3,000 is the number that we would like down the road. We are starting with an initial amount of 40. The rate that was given to us was triples, so we know that the base is 3. Then we had a rate given to us, and that was that they triple, but they take 2 weeks in order to triple. Okay, so now the unknown value, which is the number of weeks, goes there. Okay, so now we can just go ahead and solve this as we would normally. So first thing I'm going to do is I'm going to take and move the 40 over to the other side so I can isolate this base. So I'm going to take the 3,000 and divide it by 40. That is going to be equal to 3 to the exponent w over 2. Okay, now I can take the log of both sides, and that will help me move this unknown variable out of the exponent back into the main line. So I'm going to write the log of, 3,000 divided by 40 is going to be equal to, I'll move the exponent down, w over 2, times the log of 3. Okay, let's continue right up here. So now I want to get w all by itself, so I'm going to move the log 3 to the other side. So we will have the log of 3,000 divided by 40 divided by the log of 3, and that's going to be equal to w over 2. Okay, well, evaluating the left side, I get 3.9299, that should be enough, is equal to w over 2. Solving for w, I just move the 2 over to the other side and multiply, and we find that w equals 7.8598, or if we round, w equals approximately 7.9, and the unit was weeks. Okay, so in this example, we were asked to find how long will it take. It's going to take approximately 7.9 weeks. But the important thing was that we had to be careful with the exponent. The exponent was represented as a fraction because they used a word triples. You might get a word doubles. And they gave us the rate, how long it takes for that tripling to happen. So if they do that, put it in the denominator and then just go ahead and solve normally. All right, let's take a look at a third and final example. And this example is going to involve decay. And in fact, it's a special type of decay because this is going to be a half-life question, and we'll see the words half-life listed right in the question there, which means that we know the base is going to be 1/2. All right, so let's just read the question. It says a researcher made 210 milligrams of a radioactive substance and found that there was only 60 milligrams of the material 12 hours later. What is the half-life of the material? Okay, so a couple things to note. The initial amount, 210, final amount, 60. The unit of time is expressed in hours, and we are told the length of time that passed. What we don't know is the half-life period. So when we set up our equation, I'll just use some color coding here. We'll use 210 as the light blue, 60 dark blue, 12 there. Half-life will be red, and we know the base. All right, so let's go ahead and get started. The researcher made 210 milligrams of a material. This is half-life, so I know the base is 1/2. Okay, at some point in the future, only 60 milligrams remained. That was the final resultant amount. We are told that it took 12 hours for that to happen. But what we don't know is we don't know the half-life period. So in this case, the x is in the bottom of the fraction. Okay, well, solving this is identical to the previous example that we just did. We just have to be careful in the last step. So as we go through this, we're just going to go and follow the same steps. So we're going to take the 60, we're going to divide it by 210 so we can get this base all by itself. So we'll just have 60 divided by 210 is equal to 1/2 to the exponent 12 over x. Now I can take the logs of both sides. So I'm going to take log of 60 over 210, and that's going to be equal to the log of 1/2, and we move the exponent down in front. Okay, well, we're solving for x, so let's get this all by itself. Move the log 1/2 to the left side. We will get log of 60 over 210 divided by the log of 1/2, and that is going to be equal to 12 divided by x. All right, well, evaluating the left side, those two logs being divided, careful with your brackets, we get that 1.80735 is equal to 12 over x. Okay, well, to solve for x, first I'm going to move x up to the left side with multiplication, so I would get 1.80735 times x, and then I divide both sides by 1.80735, which moves it underneath the 12. So I will be left with x equals 12 divided by 1.80735. Solving that on your calculator, and you get x equals 6.639, or if I was just to round, x equals approximately 6.6, and I look back for the unit of time, they were talking about 12 hours later, so this is 6.6 hours. Okay, so the half-life of the material is approximately 6.6 hours. And that's how you solve for the exponent both in exponential growth and exponential decay problems.